Hello, everybody. I have the pleasure today to introduce our speaker, our colleague, Dr. Marwa Banna from the New York University, Abu Dhabi. Dr. Banna is an assistant professor of mathematics at the New York University, Abu Dhabi. From 2016 to 2020, she was a postdoctoral researcher at Starland University, working with the Free Probability Research Group led by Roland Spitzer. Before that, she served as a senior postdoctoral researcher at Telecom Paris Tech, hosted by Walid Hashim. In September 2015, she earned this PhD from University Paris Est under the supervision of Professor Florence Merlvet and Emmanuel Rio. Thank you again, Dr. Benna, to honor us to be one of our speakers. And please, you can start our talk and apply the notions of non-commutative independence. Thank you.
Thanks so much for the invitation. It's a pleasure to be giving this talk. I will be talking today about the different notions of non-commutative independence. These topics are related to random matrices. So I will start my talk in this way. I will give a brief introduction to random matrices and then bridge this to free probability and make this connection to the non-commutative world. And then I will introduce a bit what free probability is, or what non-commutative probability is. So I will be introducing the notions of non-commutative probability spaces and all the different notions of independence that exist in the non-commutative world. And then I will tell you a little bit about the central limit theorems for each notion of independence and what can be said in this non-commutative setting. So to start, I will quickly recall what is a random matrix. A random matrix is a matrix whose entries are random variables that have a certain joint distribution. So this is a realization of one random matrix. Random matrices, this domain was born because of
Can I ask a question, please?
Yeah.
Just for the random matrix, all the components must be from the same distribution or not? The components are ID with the same.
Not necessarily. I will get to this later, but not necessarily.
Okay, thank you.
So the first appearance of random matrices where people got interested in goes back to Wishart in 1925, who is a statistician and who was looking at the covariance matrices of the Gaussian distribution. And then it was by the work of von Neumann and Goldstein. And you see here, this is a photo of von Neumann in front of the first computer ever, I think. And they were studying linear systems, and they wanted to numerically solve them and to, in a way, model the errors. So they used random for this. And the first really time where mathematicians got involved more in this topic, got the more attention from the mathematical side, was after the work of Wigner, Dyson, and Mita. So they are physicists, and they were studying some heavy nuclei. And their interest was to study the energies of heavy nuclei, and what they showed is that the spacings between the lines of the spectrum of heavy nuclei should resemble those of the eigenvalues of a random matrix that has a certain symmetry. And this is what they proved actually, and using random matrix result, they were able to do this. So I will come back to the result more in details in a few slides and tell you what is it precisely. But after this result, this domain got the attention of many mathematicians, and And I mention here a few names: Marchenko, Pasteur, Gierko, Bai, Silverstein, Tao, and Vo, and the list is really very long. And since then, this domain has become very active, and many applications to other and connections to other domains were found. So as you can see through this diagram, that random matrix theory is related to or appears in many other math domains. As you can see here, combinatorics, number theory, complex analysis, and the list is really long. And through computer science, by machine learning, neural networks, AI, complex system. It also appears through applications in biology, and of course in physics, mainly in statistical mechanics and many other topics. So some of the other applications, a few applications that I would like to mention here is also the multi-user, multiple channel in telecommunication systems. So random matrices play a crucial role to study the capacity of such channels. And since this connection was revealed, also there was lots of interaction between these two domains. And of course, as well in neural networks that can be written as functions of products of matrices of certain structure. So I won't go in the details of this, and of course, this is a list of some applications in different domains in healthcare, transportation, e-commerce, etc. So this is just to tell you a little bit about why or where random matrices appear. So what are random matrices? This is the most fundamental and basic example of a random matrix. This is a Hermitian matrix. So it has IID random variables. Of course, in other models, we can assume that the variables are dependent or not necessarily identically distributed, but for simplicity, I will stick to the most basic example here, just to tell you what might happen. So if we have this Hermitian matrix with IID random variables, they are symmetric, and we assume that they have the same variance sigma squared. One of the questions that we are interested in is the behavior of the eigenvalues of such a matrix. So in order to study the behavior of the eigenvalues, we will consider this empirical spectral measure, mu of xn, which is 1 over n, the sum of the Diracs in these eigenvalues. Of course, since this matrix is a random matrix, then the eigenvalues themselves are also random, and this mu xn is a random probability measure. And one of the things that we're interested to know is what happens to the distribution of the eigenvalues when the dimension of the matrix capital N grows to infinity. Okay, so there are many questions that people ask for such matrices. The limiting spectral distribution. What are the regularity properties of such a limiting distribution? And of course, we're also interested in quantitative estimates, like for n fixed but large enough, what would happen? The fluctuation of the eigenvalues, estimations of the spectral norm, whether all the eigenvalues are in the bulk, or do we have some outliers? Many questions here, and for different reasons, people are interested in get asked. So what are some of the factors that might affect the behavior? Of course, the structure of the matrix, also the independent structure of the entries, whether they are independent or not. What is the are they identically distributed, or do they have a variance profile, for instance? Is the matrix sparse or not? Many things would affect this distribution. And these are the things that people usually study. And then there are other universality questions similar to those asked by the physicists, is a kind of universality questions, meaning that if I start with a matrix with independent entries that's symmetric like this, if I change the distribution of the entries, what happens to the limiting distribution? Do I have certain kind of universality, or is the limiting distribution affected by our choice of distribution of the entries. So all these questions are questions that people are interested in random matrix theory. So this is a glimpse of some of the many questions that could be asked in this direction. So to give you some answers, if we assume that this matrix, I will assume for now that it is a GUE matrix, meaning that its entries are Gaussians, okay? So this will not be important, but I want to introduce the name of a GUE matrix here. So a GUE matrix is a Hermitian matrix whose entries are IID Gaussians. They are centered and of variance sigma squared. Of course, the entries that are off diagonal are complex Gaussians, but because the matrix is symmetric, then the entries on the diagonals are real Gaussians. So if we look at this empirical spectral measure, what Wigner proved in 85, and this is one of the most fundamental results in random matrix theory, is that this empirical spectral measure converges weakly to a deterministic probability measure whose density is given by this function here, and this convergence is almost sure. So I proved that almost surely this random probability measure converges weakly to a deterministic measure. And this is what we call the semicircular distribution, and it's because its density function looks like a semicircle. So as you can see here, we have universality in the sense that this result will hold even if we choose distributions other than the Gaussian distribution, as long as we assume that they are IID and that the matrix is Hermitian, we will get exactly the same result. And this is a universality result in the sense that the limiting distribution does not depend on the initial distribution of the entries except through the variance sigma squared. So this is indeed a universality result. And if we, for example, plug the histogram of the eigenvalues of this matrix, we can see that it starts to take this semicircular shape. Okay, so this is a simulation to show you that for n equal 300, this is what we get, 1000. You see it's getting closer and closer, and for n equal 3000, we have almost the semicircular distribution. So now if we consider Wishart matrices, so these are Gram matrices, okay? I have this rectangular matrix of dimension n times p, and I consider 1 over n xn star, okay? Then this is a Gram matrix, or it is, if these entries are Gaussians, we call it the Wishart matrix. Then if we assume that everything is independent IID as before, and we look at its empirical spectral measure, then if we know that n over p converge to infinity at the same pace, they converge to some rho which is positive, or strictly greater than 1 in the case that I will going to show you, then this is what we will get. So this Marchenko and Pasteur proved this in 1967, and they proved that almost surely the empirical spectral measure converges weakly to the Marchenko-Pasteur distribution. And again, this is a deterministic distribution whose density function is given by the following. And you can also see that it only depends, we have again a universality kind of result here, because it only depends on sigma squared, which is the variance of the entries, and now on rho, which is the limit of the ratio of n over p. Again, some simulations show you the following. And now everything I have showed you so far are when I consider only one matrix. But the question that we would ask, what if we have more than one matrix? Let's say, let's go back to the GUE model, which is the simplest one, the first model that I showed you today. And let's assume we have two independent GUEs. And I would like to look at the limiting spectral distribution of their sum. So I want to take their sum and see how do the eigenvalues behave at the limit? Or what if I would like to look at their product? Or what if I would like to take any polynomial in these matrices and look at the limiting spectral distribution of this polynomial in a tuple of independent GUEs? So can I compute this limiting spectral distribution, and what happens in this case? And here comes the role of free probability. So free probability is important when we are considering more than one matrix, okay? Because of this fundamental result that was proven by Vokulescu, I will come later to this result again, because many ingredients are now still missing. But to tell you what Vokulescu proved, he proved that if you have a D tuple of independent GUEs, and you take any polynomial in these matrices, you take the expectation of the trace, and then you let n grow to infinity, then this will be the limiting distribution of this polynomial will be the distribution of the same polynomial p. So this is the same polynomial that we started with. But now this is the distribution of a polynomial of some operators living in some non-commutative probability space. And what is important about these operators is that they are freely independent. So we start by classically independent matrices. I have a tuple of classically independent GUEs, but at the limit, another notion of independence is appearing naturally. And in this case, it is free independence. So these S1, SD are semicircular operators, and they are freely independent among each other, and they live in a non-commutative probability space A phi. So what I will show you now, I will introduce all these notions that appear in this theorem, and I will go more into details. But what's happening here, we are starting by classical independence, and at the large n limit when n grows to infinity, and only when n grows to infinity, another notion of independence is appearing, which is free independence, and this is why we call this kind of result asymptotic freeness, because freeness is appearing at the limit. So in order to make this clear, I would introduce non-commutative probability spaces and tell you what is a free independence, and then hopefully this will become clearer. But before this result, all these concepts on free probability existed, but without this connection to random matrices. Once this observation was done, these two domains started interacting a lot and serving each other, and we started using free probability to prove results on random matrices, and vice versa, using random matrix theory to prove important results in operator algebras. So to keep the story short, I'm gonna make this little analogy between the classical and the free setting, and to give you an idea that there's an analog of the classical probability theory in the free world. So as in classical probability, we have probability spaces. In free probability, we also have a non-commutative probability space. Instead of classical independence, we have a different notion of independence called the free independence. And once we have two independent random variables, what we can do is, if we know that two variables are independent and we would like to compute the distribution of their sum, then knowing the distribution, the marginal distribution of each one of them, we can compute the distribution of the sum by the classical convolution. So there's an analog thing in the free case. If I know that A and B are freely independent and I know the marginal distribution of each one of them, then the distribution of the sum is the free convolution of mu A and mu B. Like the Gaussian random variables play a crucial and fundamental role in classical probability, the semicircular distribution plays this role in the non-commutative setting. And you've already seen in the Wigner theorem, the limiting distribution was the semicircular distribution. We have also central limit theorems. What plays the role of a Luke Fourier transform is something known as the R transform. And above all this, we have an operator valued extension of free probability that we call operator valued free probability. This I will come back to in the second part of my talk. So to define things properly, first of all, we're going to define what is a non-commutative probability space. So it's a pair A and phi, where A is a complex star algebra that's unital, and phi is a linear functional, as well, it's unital, and it is positive. And this is what will play the role of the expectation in classical probability. So this phi will play the role of expectation. And we call it, okay, so this is the state. And any element in A will be a non-commutative random variable. So example of non-commutative probability spaces, obviously the classical probability space where we assume moments, finite moments of all orders fit in this framework, and with this phi being the expectation. But maybe you would like to see a non-commutative example. So of course, if you consider matrices, complex valued matrices that are n by n, together with the normalized trace to ensure that the normalized trace of the identity is equal to 1, then this defines a non-commutative probability space. And if we're interested to study random matrices, then maybe we're going to mix these two together and consider matrices whose entries are random variables. And in this case, the expectation of the normalized trace will be this phi. So these are examples, and you can see that random matrices fit well in this framework. Now, how do we define distributions? You would ask, what is the distribution? I mentioned in my previous slide the distribution of an operator A. So what do I mean by distribution? So the non-commutative distribution of an element X of our non-commutative probability space is defined simply in terms of its moments. So the collection of all moments of X is what defines its non-commutative distribution. And how do we define convergence in distribution? So we say that Xn converges to X if all moments of Xn converge to the moments of X, to the relative moments of X. Now, if the element or of the operator is self-adjoint, then in this case, we can describe this non-commutative distribution, which is a priori defined combinatorially in terms of the moments. We can describe it using measure theory. Why? Because if the operator is self-adjoint, then we know that there is a unique real probability measure that describes its moments, that encodes these moments. So this mu X has the same moments as X, and we call it the spectral measure of X. So once we have access to measure theory, we also have access to many analytical tools that we can use and that turn out to be very powerful and give us access really to many tools in functional analysis and complex analysis that we can use in this case. One of these operators is the Cauchy transform. So the Cauchy transform is phi of the resolvent. So I'm going to denote in this talk by gx of z to be z minus x inverse. So this is the resolvent of x at point z. And the Cauchy transform will be phi of the resolvent, and it is given by the integral of 1 over z minus t d mu x of t. Why is this Cauchy transform important? Because proving convergence in distribution of xn to x is equivalent to proving the pointwise convergence of the Cauchy transform of xn to the Cauchy transform of x for any point z in C+. So if we want to prove this, then we need to prove that all moments converge. It's one way of proving some results in free probability and also in random matrices, and this approach is combinatorial and what's known by the moment method. Or if you would like to take a more analytical approach, then one of the most important tools would be the Cauchy transform by proving the pointwise convergence of the Cauchy transform. Once we prove the convergence in terms of Cauchy transform, we can also recover the limiting distribution because the Cauchy transforms characterize the measure. So if I know the Cauchy transform, I can from it recover the associated measure. So proving this on the level of the Cauchy transform reduces proving our result, proving convergence in distribution. And this turns out to be a very powerful tool to use to get quantitative estimates in particular and to prove many other things. So how about a joint distribution? So here we define the distribution of one element. But if we have now a family of elements xi, how do I define the joint non-commutative distribution? Well, it is simply the collection of all possible mixed moments in these elements of any length. So I take any word in these elements of any length, and I look at phi of this word, and the collection of all these possible mixed moments will give me the joint distribution. However, if I have more than one variable, more than one operator, there's no analytical way, or there's no way through measure theory to describe this joint distribution. So what we do is instead we look at polynomials in them. So we take, for example, a self-adjoint polynomial P in this family xi, and I look at the distribution of this polynomial in this xi, and because it's self-adjoint, I'm back to the case of one single self-adjoint operator, and this gives me access again to measure theory and all the analytical tools that I can rely on. So now we know what a non-commutative probability space is and how we define these non-commutative distributions. What is free independence? So free independence is defined in this way. It tells you that if you have unital algebras A1 up to AN, they are freely independent with respect to phi. If I take elements that are centered with respect to phi, and I take their product, whenever these elements are alternating, it means that no two consecutive elements are coming from the same algebra. Once I have this condition and the fact that they are centered, then phi of these elements is equal to 0. So Valkylisco introduced the free independence in the context of operator algebras before any connection to random matrices, while he was studying the free group factors. And you don't need to know by heart this definition. What's important about this definition is that it gives us a rule to compute moments. So in order to compute phi of AB, if I have the AIs are coming from an algebra A that's free from the algebra B. So how do I compute this moment? I simply know that A minus its expectation times B minus its expectation. I know that this is equal to 0. So I expand and then I get this. So you see that for two variables, it coincides with the definition of classical independence. Here as well, you see that we still coincide with the classical independence definition. But from this example, you can see that it is different. So this is a different notion of independence, okay? And this gives us a way of computing moments. Of course, we can always compute moments iteratively by relying on lower order moments, but there's a straightforward way of doing this through what's called the moment cumulative formula. I will not discuss this here. So this free independence that was introduced in an algebraic operator algebra context appeared naturally in the context of random matrices. So here we started by a tuple of independent matrices. We ended up by a tuple of freely independent semicircular elements. And now, because I have all these notions of convolutions, so if I know that S1 and S2, for example, are freely independent, I know both of them are semicircular, so I know their distribution. And using the free convolution, I can get the distribution of their sum. Or through the multiplicative convolution, I can get the distribution of their product, etc. So we can describe this instead of looking at the limiting spectral distribution in terms of the limit of some matrices. I forget now about the matrices, and I focus on these operators that are nice and that we know a lot about, and we have lots of tools through free probability and operator algebras that allow us to study them and determine many properties of them. And then whatever we conclude here, we can pass to the matrices. So this is one way of seeing things. But the news is that free independence, or the notion of free independence, is not the only notion of independence that exists in the non-commutative setting. So we have different notions of independence. We have in total 5 notions of independence. So tensor independence, which is the classical independence. You have seen now free independence. I will still introduce the Boolean independence and the monotone independence and its mirror symmetric image, the anti-monotone independence. And for each notion of independence, I will show you other matrix models where these notions of independence appear naturally at the limit. So let's move to the Boolean independence. Boolean independence is relatively defined in an easy way. So if we have algebras A1 up to AN, here they don't necessarily need to be unital. We say that they are Boolean independent if I take elements A1 up to AN from different algebras that are no two consecutive operators come from the same algebras, then things factorize in this way. Of course, these are non-commutative variables, so I need to have the same order. But then this will factorize like this, and this phi, these now are complex numbers. So this is the definition of Boolean independence, and again, it gives us a rule to compute moments of Boolean independent variables. So you see that this is really very simple. You just take the product. Phi of the product is the product of phi of each element whenever they are coming from Boolean independent algebras. How about a matrix model where this notion appears naturally? So, for example, if you consider this n by n matrix AN and you divide it into 4 blocks. So the first block here will be of dimension n0 times n0, which is fixed, okay? And then this block here will be n minus n0. So if you define now T of AN to be the matrix where you replace the diagonal blocks by zeros and you keep the off-diagonal blocks as they are. And we define now a new trace. It's not the normalized trace like the one we defined before. It is called the partial trace, and it is 1 over n0, the expectation of the trace of the first block. So if I want to look at the partial trace of a matrix AN, I take this first block A11, and I take the expectation of its normalized trace. And this is what we call the partial trace. And what was shown that if n0 is fixed and you pick AN and BN to be independent GOE matrices, then TAN and TBN are asymptotically Boolean independent with respect to this partial trace. So here Boolean independence appears at the limit, not free independence. And what do we mean by this asymptotic Boolean independence? It means that there is a star probability space and 2 elements A and B that are Boolean independent with respect to this state, such that T of AN, TBN converges to AB in distribution. What do we mean by convergence in distribution? It means convergence of all possible mixed moments. So I can write it in terms of any polynomial. So if the partial trace of any polynomial in these two matrices converges to the distribution of the polynomial of A and B, and A and B happen to be Boolean independent, this is what we call asymptotic Boolean independence. And this is what happens for this model. So this notion of independence appears at the limit. And also Camimal provided another matrix model for asymptotic Boolean independence with respect to the antitrace, but I will not discuss this here. Now the monotone independence. So we say that A1 up to AN is a family of sigma algebras of A that are not necessarily unital. Unlike the free and the Boolean case, here we have an order on the algebras in the monotone independence case. And you see we denote it by this. By this writing, we say that A1 is monotone independent from A2, A2 is monotone independent of A3, etc. If this condition is satisfied. Okay, I will not read this definition closely, but I will give you an example to show you how this works. So with this rule here, we can also compute moments. And you can again see that this is a different notion of independence than the other two that we have seen. And to give you an example of how we can compute using these rules the moments, let's assume that I have, for simplicity, only three algebras, subalgebras that are monotone independent. The little ai's are elements of A, the bi's elements of B, and the ci's are elements of C. And I would like to compute this moment. So how this rule translates here, here you have A, B, and C. You have this order on them. So all elements from A, I put them in this lower level. Then the elements from B, I put them here, and the elements of C. And then I start by subtracting the summits. So here I have a summit, and here I have a summit. I factorize them, I take them out, and I get phi of C1 and phi of C2. And what remains after removing these summits are these. Okay? And now in the second step, I continue by removing summits, and I get this one and this. And what remains is these i's here. So for some reasons, in my ordering, I passed from A1 to A3, but it's fine. Okay, so this is monotone independence and matrix model associated to this notion of independence. Again, if I consider the same matrix TAN, where I replace the block diagonals by zeros, and again, I have the partial trace. So it has been proven by Lenshevsky in 2014 that if I pick AN and BN to be independent GUEs, here when I say independent GUEs, I mean classically independent GUEs, and I consider TAN and BN. In the Boolean case, it was TAN, TBN. So now TAN and BN, then they are asymptotically monotone independent with respect to the partial trace. And recently, after more results, we have much more models that where the monotone independence appears asymptotically. For example, if you take AN to be a GUE and BN to be any permutation of AN with some conditions on the permutations, but in particular, you can choose BN to be AN transpose. You see that here, these two matrices are no longer independent if I take AN and AN transpose. But still, when I look at this, I have asymptotic monotone independence. And also, a recent result showed for more general matrices, matrices that are like the GUEs, but whose entries are not necessarily Gaussians. They can have any distribution they want, but this is under some moment conditions. Then also we have monotone independence appearing in the limit when I consider this pair. And what do I mean by monotone independence? It means that there exists some star probability space and elements A and B in this non-commutative probability space that are monotone independent, such that TANBN converges to AB in distribution. In other words, if I take any polynomial in TANBN and I look at the limit of the partial trace, I will get psi of P of AB with A and B being monotone independent. Now, since I know that AB are monotone independent, I can compute the distribution of their sum, of their product, etc. So the most natural polynomials to consider are the commutator and anti-commutator. And in the free case, their distribution has been found by Nika and Speicher, and then it took, as you can see, a long time in order to do the anti-commutator case. And in the Boolean and case, it was done in 23, and lately, and we filled this gap and completed the picture, and we have found the distributions of commutator and anti-commutator when A and B are monotone independent. We also do it for more general polynomials. They can be, for example, any linear span. So depending on what values of alpha and beta you take, you recover the commutator and anti-commutator, but also a slightly more general form of polynomials. So in this paper with my postdoc Paimon Tseng, we find a way to find the distribution of such polynomials. And when I say distribution, it means we were able to give explicit description of all moments of such polynomials. And you don't need to worry and read all these, but what I would like to tell you is that we can, using these results, deduce things on random matrices. So if I have AN and BN independent n by n Wigner matrices that satisfy some moment conditions, I'm hiding the details in this announcement, and we consider a polynomial Pn defined in this way, then we know that the limiting distribution of Pn with respect to the partial trace is given by this distribution. So here it's half the Dirac measure in omega plus the Dirac measure in minus omega, with omega is this term that depends on the Catalan numbers, and the Catalan numbers are the moments of the semicircular distribution. So using tools from free probability, we were able to deduce such results on random matrices. And here, this is another example of another polynomial in such matrices. So once I know that these matrices are independent at the limit, whether it was free independence, monotone independence, Boolean independence, any notion of independence you have, you can compute the distribution of polynomials in that. So if you would like to study more general polynomials, here we would need more advanced tools, and we would need the operator valued framework. So as I told you at the beginning, we have the non-commutative. I showed you the free setting, and I said on top of it, we have an extension, an operator valued extension of this. And now I will try to convince you or tell you one of the reasons why this operator value setting is important. Of course, it's studied for many other reasons, but this is one motivation of why we are interested in this operator valued setting. So let's say we have a polynomial, and I will stick now to the free case because it's the most known and maybe people are the most familiar with it, and we know much more in the free case than in the other cases. So I have a polynomial and freely independent random variables, of course, non-commutative random variables. This non-commutative polynomial looks like this. So here I have monomials in these non-commutative random variables, and they are multiplied by complex numbers. If I would like to study the distribution of this polynomial, here I'm dealing with a non-linear function, okay, in variables that do not commute. So the difficulty of the problem is really high, because at the time I have to deal with a nonlinear function, but in variables that are non-commutative. So one way of approaching such things is to linearize the polynomial. It's called the linearization technique. And instead of considering this nonlinear polynomial, we will consider a linear polynomial in the variables x1 up to xt. But now the price that I pay is that the coefficients are matrix valued. So I start by complex valued polynomials, but that are nonlinear in my variables. I linearize it, so now I have a linear polynomial in x1 up to xd, but at the price of having matrix valued coefficients. But with this nice observation, as I told you, knowing if we want to know the distribution of this polynomial, it's equivalent to look at the distribution of its Cauchy transform. So it turns out that we have this nice relationship between the Cauchy transform of our original polynomial and the Cauchy transform of this, or something similar to the Cauchy transform of this linearization. And it is the following. The Cauchy transform of our polynomial is the 1-1 entry of the Cauchy transform of the linearized polynomial. So great, now I can work on this linearization and pick the 1-1 entry to know the Cauchy transform of the polynomial of my interest. But now I'm no longer working in the framework of M phi. I'm working in the framework of MM of n. So now I have, so if these matrices here, the coefficients are m by m matrices, now my polynomial, it is now no longer in M phi, but it is in MM of m. And now the state, to make it a non-commutative probability space, is the normalized trace tensor phi. And you see this in red because this is what's appearing here. So what is this? This is not a trace, okay? It is what we call the conditional expectation. So, and this is an element of an operator valued probability space. I will give you the definition now more precisely, but just to sum up what's here, I start with a polynomial with nonlinear coefficients. We use the linearization technique to get a linear polynomial in these variables, but at the price of paying, of having matrix coefficients. But if these elements here are free, freeness is conserved here, but it's not freeness over M phi with respect to phi. It will be freeness with respect to this mapping here, that is the conditional expectation. And for this, we need to go to this operator valued or to this matrix valued extension of free probability that we called operator valued free probability. How much time do I have to know how much details I can go with?
3 minutes.
Okay, then I will not do this. I will just tell you that this is one of the reasons why we have this operator valued extension. Maybe what would be interesting for the remaining part of this talk is to tell you more about the central limit theorems for the different notions of independence. So in the classical setting, we all know that if we have IID random variables, then by the central limit theorem, we know that this 1 over square root of n of the sum of x1 up to xn converges to the Gaussian distribution. Well, in the free setting, if we assume that these variables are freely independent, then what we obtain at the limit is the semicircular distribution. So in terms of moments, This is equivalent to saying that the kth moment of the sum converges to the moments of the Gaussian distribution, and in the free case, it corresponds to the moments of the semicircular distribution. Now, in the Boolean and monotone independence, we have other distributions appearing at the limit. In the Boolean case, it is this Bernoulli element that's appearing, and in the monotone case, it is the arcsign element. And why do we call them Bernoulli and arcsign elements? Because their distribution, here it has the Radmacher distribution. As you can see, we have half the Diracs on -1 plus the Dirac on 1, but we call it Bernoulli element. So it has the moments of a Radmacher. And here in the monotone case, the limiting distribution, it has the same moments as the arcsign distribution. That's why we call it the arcsign element. So as in the classical setting, we're interested in quantifying the rates of convergence in the central limit theorem. So in terms of the Kolmogorov distance, we know that in the classical setting, we have convergence with the rate 1 over square root of n, and we need that the moments of third order to exist. In the free setting, we get the same rate of convergence, but here we need the fourth moment as well to exist. In the Boolean setting, we have the fourth moment and a different rate of convergence. And in the monotone setting, we have this rate. So what we do in the one of the other interests that I have is the central limit theorem, but in the operator valued setting that I didn't have the chance to tell you about it in details. But maybe I will show you one results about the things that we are interested in. So we obtain, sorry, assumed I have much more, or I would go faster. It wasn't the case. I can't remember where the slide is. Okay, so here. So one of the things we're interested in are obtaining such quantitative estimates as well for the operator valued setting. So in the operator valued free setting, we also have an operator valued central limit theorem, and its limiting distribution is not the semicircular element, but what we call the operator valued semicircular element, which I denote here by Sn. And we also quantify the convergence in terms of the Levy distance, and this is the rate that we get. We don't assume that this rate is optimal. In the classical case, it was 1 over square root of n. This is what we obtain here. We don't say it's optimal, but this is the only quantitative estimate that exists so far in the operator value setting. And in some cases, we're able to pass these results to the Kolmogorov distance as well. And now we have some works where we consider the Wasserstein distance, which is also a stronger form of convergence. So what I showed you here was for the free case, but we also do the study the operator valued Boolean and operator valued monotone independent case. And related to such works, we are now doing similar kind of studies for another notion of independence that's called the C-free independence. But here, as you can see, you have two states instead of one state. And we also have the multiplicative central limit theorem in the free case. And unlike in the classical setting, one can deduce the multiplicative central limit theorem from the additive central limit theorem. But in the non-commutative setting, it's not the case. And it has to be studied on its own. And of course, in the multiplicative setting, things get even more complicated. So these are joint works that are in progress that will appear soon with my postdocs here at NYU AD. And this is everything I would like to tell you for today, and we'll stop here. I skipped a lot, but...
Thank you, Dr. Banna, for this nice talk.
Thank you.
Are there some questions, please? Some questions, please. So we have present an equivalent to the central limit theorem for the free probability. Okay. And you have replaced N01 by S01. Are there some equivalent to the strong law of large numbers or strong law of large numbers for the free probability?
Yeah, there are laws of large numbers, but just to say something that in free probability, it's always an expectation.
Okay.
So usually, if I go back, for example, when I gave you this result on asymptotic freeness, so here it's stated the expectation of the trace conversion to this.
Okay.
So it is always deterministic, and how we pass to the almost sure case is by some kind of notion of concentration inequality. So in free probability, everything is an expectation in a way.
Okay.
So we have the law of large numbers, but it is with respect to this phi. Okay. So usually we prove results like this in expectation, and of course in random matrix theory we want stronger forms of convergence. We want almost sure convergence or some stronger form of convergence. Then we get it through usually concentration inequalities or But free probability we only deal with expectations.
Okay, so we don't deal with the conditional expectation or martingale or something like that.
Oh, no, of course. This is the operator valued part that I couldn't go in details to it. So let me go back just quickly because you asked. So when we define this operator valued probability space, it has this BB bimodule map from A to a subalgebra B of A. Okay. So this will play the role of the conditional expectation.
Okay.
And freeness or independence with respect to the conditional expectation follows exactly the same rule as freeness with respect to phi. But here, because the outcome is an operator, things are still non-commutative. So this phi of B is a complex number, but this E of B is an operator. So you need to keep track of the order. So it's exactly the same rule, but you need to keep track of the order. That's why you have this nested version of it. So if you compare this, phi of AB, ABA, it's phi of A squared, phi A, phi B squared. So if I look at it with respect to E, this is phi corresponding to phi of A squared. So this is the second moment of A with respect to E. This is phi of A, and this is the second moment of B. But you have this nested form because they don't commute, so you need to keep track of the order, unlike here. Okay, so this is the notion of conditional expectation. You have notion of martingales, you have free stochastic calculus, many things. You have free Brownian motions. Yeah.
And what about the applications compared to the classical probability?
Yeah, so free probability. Mostly, if you'd like to look at applications for it, nowadays many connections are appearing through quantum information theory, for example. Of course, random matrices, I made the connection clear. It's also appearing in questions, again, through random matrix theory, but in machine learning and in neural networks. So people are starting to figure out more and more connections to free probability. So as of applications of free probability, it serves like a tool to prove things, for example, on random matrices, to prove things in quantum information theory, etc. And the power of free probability is when you have more than one matrix, for example. So if you want to study one matrix, like the first two slides of this talk, you use tools from classical probability. And these results were done before using classical probability. But once you want to look at distributions, for example, of more than one matrix at the same time, then it's convenient in many situations to look at the whole matrix as a non-commutative random variable itself, the matrix itself as a random variable. And here you are dealing now with non-commutative random variables, so it falls in the framework of free probability, which gives you many tools to compute distributions, to look at regularity properties of these distributions. Free probability was a very also important tool to prove very deep results in operator algebras, for example. So this is how I see it. It's really at the intersection of many things, and it provides very nice approaches and different perspectives for several questions.
When you talked about the monotone independence, if you can go to the slide where there are monotone independence. You define mu x equals to phi xi1, xi2 up to xik.
Sorry, this slide?
Okay, for example, this one. AI, you are sure that AI is unique. Okay?
What do you mean? I mean, these subalgebras, they are not necessarily unital.
No, after the monotone independence, we say that phi A1, A2, AI equals to phi AI. What is I? How we can choose the index I here?
No. It's telling you that whenever you have AI coming from an algebra, like an AI that's a summit. Like here, I didn't read this because it might not be very clear from directly. That's why I gave this example. What this is telling you, whenever you have AI coming from an algebra, and AI is here in this word is located between AI minus 1 and AI plus 1, with AI and AI plus 1 are from algebras that are less than the algebra AI, then you can put this in expectation and put it factorize it outside. So it's explaining the rule of how you compute moments. So these definitions of independence, they give you the rules that you need to compute moments of independent variables. Okay. And in this case, what is playing the role of AI is this C, because you see it's located between two elements coming from an algebra that is less than C.
Okay.
Okay. So whenever you are in such situation, you take phi of these elements and you pull them out.
Okay.
And then once you pull them out, you get to this situation here. So now which elements, all these B1, B2, B3, they come from one algebra B. So I can call them B tilde, okay? And then this B tilde is surrounded by two elements coming from A. So I take phi of them, and I take it out of the product. And similarly to this before here, it is between two elements that are coming from the algebra A. And after I extract all these, what remains are the A's. So they are together.
Okay.
So this is just a rule that allows you to compute the moments. Yeah. And you can see that you can, like here, I started by the product of two elements, then I'm going to higher order moments. And these higher order moments, you can always deduce them from the lower order moments. So it gives you an iterative way to compute the moments. Of course, it's not what we do anytime we want to compute a moment. There is a more straightforward way by using the moment cumulant formula over some lattices of non-crossing partitions that allow you to, through the moment cumulant formula, to obtain such expressions.
Okay. And please, if you can go to the previous slide.
This?
No, go again. No, a slide where we have mu x equals to phi xi1, xi2 up to xik.
The Boolean one, you mean?
No, mu x. Okay. When you have mu x equal to the system or the set phi xi1, xi2. Okay.
Which slide do you remember what I was talking about?
Not the previous, the next slide.
The next?
Maybe. No. No. Okay. No problem. Okay. No.
Sorry,
Are there other questions, please? If no other questions, we have to thank again Dr. Marwa Banna for this nice talk. Thank you to all the public, and see you after 2 weeks. Thank you.
Bye.